The year is 1941. Deep inside a Michigan factory, two engines are about to change the course of human history. But nobody in that room knows it yet. Not the engineers sweating over test stands. Not the executives watching from the observation deck. Not even the British delegation that flew across an ocean to witness this moment. They're all staring at what looks like just another pair of aircraft engines. What they can't see is that hidden inside those aluminum castings, beneath the intricate maze of fuel lines and ignition wiring, is a secret that will determine who wins World War II. The secret isn't about horsepower, it's not about fuel efficiency or top speed. It's something far more revolutionary, something that will force the world to completely rethink what mass production actually means. Because these engines sitting on Detroit test stands are about to prove that America can do something everyone said was physically impossible. August 2, 1941, Packard Motor Car Company's East Grand Boulevard plant in Detroit, Michigan. The air smells of machine oil and ozone. Two Rolls-Royce Merlin engines sit mounted on test stands, their 12 cylinders gleaming under the factory lights. British engineers stand alongside their American counterparts, clipboards in hand, expressions carefully neutral. This is the moment when American industry either proves it can match British precision engineering or fails spectacularly in front of witnesses who cross the Atlantic specifically to watch. Then the Merlins roar to life with that distinctive howl that would soon become the soundtrack of Allied air superiority. But something is different about these engines. Something the crowd can't quite identify. These aren't British-built Merlins shipped across the ocean. These are American-made copies, manufactured in Detroit from British blueprints that Packard's engineers spent 11 months completely rewriting. Every single one of the 14,000 parts inside these engines has been reimagined, respecified, and manufactured to tolerances tighter than Rolls-Royce themselves demanded. Even the thread pattern on every bolt and nut has been painstakingly replicated from Britain's arcane Whitworth system that most American engineers had never even seen before. They've taken a hand-fitted luxury engine that required skilled craftsmen to individually adjust every component and turned it into America's most mass-produced aircraft power plant. And they did it by simultaneously honoring every sacred rule Rolls-Royce held dear while breaking every assumption about how precision engineering could be manufactured. This is the untold story of an engineering revolution. Not a story about fighter aces or bombing raids. Not about tactics or strategy or military leadership. This is about something far more difficult than winning battles. Converting 14,000 precision parts from imperial measurements to American mass production standards without losing a single horsepower, without compromising a single tolerance, without making the engines 1% less capable than the hand-built originals. How they did it would change manufacturing forever. The United States Army Air Forces has a beautiful fighter aircraft called the P-51 Mustang. North American aviation designed an absolute masterpiece of aerodynamics. Pilots who fly it at low altitude call it the finest fighter plane ever built. But above 15,000 feet, that masterpiece transforms into a struggling, gasping liability that might as well be a flying coffin. The problem isn't the airframe. The Allison V1710 engine powering the early Mustangs uses a single-stage supercharger. At sea level, it produces respectable power. But as altitude increases, as the air gets thinner, that single-stage supercharger simply cannot compress enough oxygen to maintain combustion efficiency. By 25,000 feet, where German Messerschmitts and Focke-Wulfs operate with ease, the P-51 Mustang is down to barely 1,000 horsepower. By 30,000 feet, it's essentially helpless. The climb rate becomes pathetic. The B-17 Flying Fortresses and B-20 for Liberators carrying out daylight bombing raids over Germany cruise between 25 and 30,000 feet. That's the sweet spot for bombing accuracy. High enough to reduce anti-aircraft effectiveness, low enough to actually see targets through the bombardier's scope. Those bombers desperately need escort fighters that can operate at precisely those altitudes. August 17, 1943, the raid on the Messerschmitt factory at Regensburg and the ball bearing plants at Schweinfurt. 376 heavy bombers take off from English airfields. They're gambling that formation defensive fire will be enough. It isn't, not even close. The Luftwaffe knows exactly what they're doing. They climb above the bombers, beyond the range where Allison-powered Mustangs can follow, and they wait. 60 bombers don't come home. 60, that's 600 men killed or captured in a single mission. Tail gunners describe watching German fighters operating with complete impunity above the bomber formations, knowing there's nothing American fighters can do about it. The Luftwaffe has figured out the Allison Mustang's fatal weakness. The Army Air Forces needs a solution, not a new fighter. They need an engine that can breathe at altitude. They need the Merlin. Their Merlin engine is powering Spitfires and Hurricanes to altitudes the Allison can only dream about. The secret is a two-stage, two-speed supercharger system designed by a brilliant engineer named Stanley Hooker. The first stage compresses incoming air. The compressed air gets cooled in an intercooler. Then the second stage compresses it again. At altitudes where the Allison is gasping, the Merlin is still delivering over 1,200 horsepower. Every Rolls-Royce Merlin is essentially hand-built by craftsmen who learned their trade through years of apprenticeship. 14,000 individual parts, each one carefully fitted. When a connecting rod doesn't quite match the crankshaft journal, a skilled worker takes a file and makes it match. When cylinder heads don't sit quite flush against blocks, machinists lap the surfaces by hand until they seal properly. The British standard Whitworth thread system used throughout the engine adds another layer of complexity. Every bolt, every nut, every threaded connection uses a 55-degree angle thread form with unique radiused roots and crests. These aren't mass-produced fasteners. These are precision components manufactured to exacting specifications that predate modern standardization. That's the thickness of a human hair divided by 4. At that scale, temperature variations matter. Humidity matters. The phase of the moon practically matters. Cylinder heads are individually matched to blocks. Supercharger impellers are balanced by hand, with craftsmen adding or removing microscopic amounts of material until they spin perfectly true. Crankshafts are measured, fitted, measured again. This isn't manufacturing in the American sense. This is art. This is craftsmanship at the highest possible level, and Britain cannot make them fast enough. Spitfires and Hurricanes are scrambling multiple times per day, their Merlin engines screaming as they claw for altitude. Rolls-Royce's shadow factories in Crewe, Manchester, and Glasgow are running 24 hours a day, 7 days a week. Workers are sleeping in the factories between shifts. They're producing roughly 200 engines per week. They need 2,000. The mathematics are brutal and simple. British factories at maximum capacity cannot produce enough engines to defend Britain, let alone support a wider war effort. If the United States enters the war, and everyone knows they eventually will, American aircraft will need thousands upon thousands of high-altitude engines. The British government looks across the Atlantic. Could American manufacturing help? Could Detroit's legendary mass production capability be applied to precision aircraft engines? But what they do and realize is that they're about to ask American industry to perform an engineering miracle that appears mathematically impossible. They're about to ask Detroit to convert precision craftsmanship into assembly line manufacturing without changing a single dimension, without losing a single horsepower, without compromising a century of Rolls-Royce engineering tradition built on hand, fitting, and skilled labor. The real challenge is translating an entirely different industrial philosophy into the language of American mass production. It's about taking a system designed around individual craftsmanship and reimagining it for perfect interchangeability. It's about respecting tradition while revolutionizing process. And nobody is certain it can actually be done. Inside those crates are complete Merlin engines, disassembled into their 14,000 individual components. There's also a licensing agreement worth $130 million, an astronomical sum for 1940. That's more money than most people can conceptualize. It's enough to build entire factories, and it represents Britain's desperate hope that American manufacturing genius can solve their production crisis. Packard Motor Car Company isn't an obvious choice for this contract. They build luxury automobiles, beautiful, expensive cars driven by wealthy Americans. They're not aircraft engine manufacturers. They then never build anything designed to operate at 30,000 feet while producing over 1,000 horsepower for hours at a time. But Packard has something Rolls-Royce desperately needs. They have American manufacturing expertise. They understand mass production in ways British craftsmen never had to consider. They know how to make thousands of identical parts that fit together perfectly without skilled workers filing and adjusting everything. The moment Packard's engineering team opens those crates and examines the blueprints, they know they have a problem. Actually, they have approximately 14,000 problems, one for each part in the Merlin. The first problem becomes apparent immediately. The measurement systems are incompatible. Britain uses imperial measurements, but not the same imperial system America uses. This isn't a simple conversion like changing kilometers to miles. Rolls-Royce specifies dimensions in thousandths of an inch, but their baseline standards come from British engineering traditions that predate modern standardization. Converting these to American specifications isn't simple mathematics. It requires understanding the intent behind every tolerance, the reason each dimension was chosen, the engineering logic that connects everything together. The second problem is worse, the British standard Whitworth thread system. Every single bolt, every nut, every threaded connection throughout the entire engine uses a 55-degree angle thread form with radius roots and crests. American unified fine threads use a 60-degree angle with flat roots. They look similar, they're close to the same size. But they are absolutely not interchangeable. If you try to thread an American bolt into a British nut, you'll cross-thread it and destroy both components. Packard will need to manufacture every single fastener in-house using British specifications. They'll need to create entirely new tooling, train machinists in a thread system most have never seen, and maintain compatibility with British-built engines and spare parts used throughout the Royal Air Force. The third problem is the big one. The one that makes British engineers skeptical that Americans can actually do this. Rolls-Royce's tolerances are designed for hand-fitting. When British workers assemble a Merlin, they expect to adjust components as they install them. A bearing clearance of plus or minus several thousandths of an inch is acceptable because a skilled craftsman will make it fit properly. A cylinder head that sits slightly crooked will be lapped until it seals. A connecting rod bearing that's a bit tight will be filed until it's perfect. Detroit doesn't work that way. American automotive production requires perfect interchangeability. The entire philosophy of the assembly line depends on it. Any component must fit any engine, period. No filing, no adjusting, no skilled craftsman spending hours making it work. Parts arrive at the assembly line and click together with mechanical precision. That's how Henry Ford revolutionized manufacturing. That's how America builds automobiles faster and cheaper than anyone else in the world. But can that philosophy produce engines with tolerances measured in 10,000ths of an inch? Can mass production achieve precision? The British engineers are polite but deeply skeptical. They've spent decades perfecting hand craftsmanship techniques. They know what Merlins require. Can American factories, geared for mass production of automobiles, really maintain Rolls-Royce standards? Can assembly line workers, without years of apprenticeship, produce engines that perform as well as hand-built originals? The unspoken question hanging in the air is whether American industrial efficiency will sacrifice the precision that makes Merlins great. Jesse G. Vincent, Packard's lead engineer, studies the blueprints for several days. He consults with his team, they run calculations, examine tolerances, analyze every specification. Then Vincent gives the British engineers an answer that nobody expects. An answer so surprising that the room goes completely silent. He says, "Your tolerances are too loose for us." The British engineers look at each other. Toulouse, the Merlin has some of the tightest tolerances in aircraft engine manufacturing. How could they possibly be Toulouse? Vincent explains. American mass production doesn't work with loose tolerances. It works with extremely tight tolerances applied consistently. Rolls-Royce allows variation because they expect hand-fitting. Packard cannot allow variation because they need perfect interchangeability. So Packard will build Merlins to tighter specifications than Rolls-Royce uses. Every part will be exactly right, not approximately right. The Americans aren't going to copy the Merlin. They're going to improve how it's manufactured while keeping its performance DNA completely intact. What happens next becomes legendary in engineering circles. Over 11 months, Packard engineers create 6,000 new technical drawings. Not because the British blueprints are wrong. They're not wrong. They're brilliant. But they're incompatible with mass production philosophy. Every dimension is respecified. Every tolerance is tightened. Every manufacturing process is reimagined for the assembly line. But here's the genius. Here's what separates this from simple copying. Packard doesn't just tighten tolerances randomly. They analyze why each tolerance exists. They understand the engineering principles. Then they create manufacturing processes that maintain those principles while enabling mass production. Take the crankshaft bearings. Rolls-Royce uses a copper lead alloy that requires careful break-in and frequent inspection. It works, but it's finicky. Packard's metallurgy team, drawing on American aircraft engine research, substitutes a silver lead alloy with indium plating. The silver provides better load-carrying capacity under high stress. The indium creates a microscopically smooth surface that reduces friction and improves break-in characteristics. The result is bearings that actually last longer and run cooler than the originals. British engineers initially object. This isn't the Rolls-Royce specification. This is American tinkering with a proven design. But when testing shows the Packard bearings outperform the originals, Rolls-Royce quietly adopts the American innovation for their own engines. That's not defeat, that's collaboration. That's engineering transcending national pride. The thread problem seems insurmountable. Packard cannot simply switch to American threads. That would make engines incompatible with British aircraft and spare parts used throughout the Royal Air Force. Every field maintenance depot in Britain uses British standard Whitworth tools. Every replacement part in inventory uses BSW threads. Changing the thread system would create a logistics nightmare that could ground aircraft at the worst possible moment. So Packard does something extraordinary. They create entirely new tooling to manufacture British standard Whitworth threads to American automotive precision standards. Think about what this means. Every tap, every die, every thread cutting tool must be custom manufactured. These aren't standard items you order from a tool catalog. Packard purchases specialized thread measuring equipment from Britain. They train American machinists in a thread system most had never seen before. BSW for coarse threads, BSF, British Standard Fine, for precision connections. British Association, for small instrument fasteners. The learning curve is steep. Machinists accustomed to unified fine threads must retrain their hands and eyes for a completely different system. The result is something unprecedented. Packard-built Merlins use exactly the same thread specifications as Rolls-Royce engines. You can swap parts between Detroit-built and Derby-built engines without hesitation. A maintenance crew in Britain can work on a Packard Merlin using the same tools they use on Rolls-Royce Merlins. But here's what makes it revolutionary. Packard manufactures those British threads to tighter tolerances than Rolls-Royce does. Every fastener is precisely within specification. No hand fitting required. Perfect interchangeability. The Americans honor British tradition while achieving American consistency. Then comes the supercharger, the heart of the Merlin's high-altitude performance. The reason Spitfires can fight at 40,000 feet. The two-stage, Two-speed supercharger system uses two impellers on the same shaft driven through gear trans. In low-speed mode, the gear ratio is 6.391:1. In high-speed mode, activated by a hydraulic clutch above a certain altitude, it jumps to 8.095:1. This is precision engineering at its finest. Those impellers must be manufactured and balanced to tolerances measured in 10,000ths of an inch. At operating speed, they spin at over 30,000 revolutions per minute. The slightest imbalance will cause vibration. Vibration causes fatigue. Fatigue causes catastrophic failure. A supercharger impeller coming apart at 30,000 RPM will destroy the entire engine in milliseconds and probably kill the pilot. There's zero margin for error. Rolls-Royce balances impellers by hand. Skilled workers mount them on precision spindles, spin them up, feel for vibration, then add or remove tiny amounts of material from the impeller blades until it spins perfectly smooth. It's time-consuming. It requires years of training to develop the sensitivity to detect microscopic imbalances, but it works. Packard develops precision casting and machining techniques that produce impellers so consistently accurate they require minimal balancing. They create dedicated test equipment that measures dynamic balance while the impeller is actually spinning at operational speed. The result is faster production and more consistent quality. The intercooler system poses another challenge. Compressing air generates tremendous heat. The laws of thermodynamics are unforgiving. Compressing air to twice atmospheric pressure raises its temperature to over 200 degrees Celsius. Hot air is less dense. Less dense air carries less oxygen. Less oxygen means less power and higher risk of detonation. The Merlin uses an intricate cooling system with passages cast into the supercharger housing and an additional intercooler core between the supercharger outlet and the intake manifold. 36 gallons per minute of ethylene glycol coolant circulates through the system, carrying away excess heat. Packard redesigns the coolant passages for more efficient flow and easier manufacturing without compromising cooling effectiveness. They use computational fluid dynamics principles before computers exist, working with scale models and pressure testing to optimize flow patterns. The result cools more effectively with simpler manufacturing. Every single system receives this treatment. Analyzed, reimagined, improved for production while maintaining or exceeding performance. The fuel injection system, the ignition system, the valve train. The oil circulation system, nothing is simply copied. Everything is understood, respected, and optimized. August 1941, exactly 11 months after signing the licensing agreement, Packard is ready. The first V1650, Packard's designation for the Merlin XX variant, runs on a test stand at the East Grand Boulevard plant. Engineers monitor oil pressure, coolant temperature, manifold pressure, RPM, everything looks perfect. The engine runs smoothly, without vibration, producing full-rated power. British observers watch carefully. They've been skeptical, they've had doubts. They've wondered whether American mass production could match British craftsmanship. The engine answers every question. Winston Churchill reportedly wept when he received the cable from Detroit. Britain would get the engines they desperately needed. The United States could now enter the war with high-altitude fighters. Allied air superiority became possible. But making one engine work is different from making 55,000 of them. Packard transforms their factory into a precision engineering marvel that would have seemed impossible a year earlier. The production line for the V1650 uses dedicated machining centers, each configured for specific operations: crankshaft machining stations, block face milling stations, cylinder head stations, supercharger assembly stations. American automotive mass production philosophy demands that every operation be repeatable and measurable. Statistical process control ensures consistency. If a crankshaft main bearing journal needs to be 2.295 inches in diameter, every crankshaft that comes off the line measures exactly 2.295 inches. Not 2.292, not 2.298. Exactly right. Every single time, a Packard line worker doesn't need years of apprenticeship. They need good training and excellent machinery. The machinery holds tolerances. The machinery ensures consistency. The machinery makes mass production of precision components possible. Workers monitor the process, make adjustments, inspect results. But the heavy lifting of maintaining microscopic tolerances falls to the machines themselves. Production ramps up through 1942. By 1943, Packard is producing engines faster than North American aviation can build airframes to put them in. At peak production, the Detroit plant completes approximately 400 engines per week. That's double Rolls-Royce's entire British output from all their factories combined. 400 engines per week means more than one engine every hour of every day, including weekends. It means over 20,000 engines per year pouring out of a single factory complex in Detroit. The V1650-3, based on the advanced Merlin 63 with improved high-altitude performance, becomes the engine that transforms the P-51 Mustang into the war-winning escort fighter that historians will write about for generations. That two-stage supercharger can maintain over 1,200 horsepower at 40,000 feet. At altitudes where the Allison wheezes and struggles, where German fighters used to operate with impunity, the Merlin-powered Mustang dominates completely. The most produced variant, the V1650-7, powers the iconic P-51D with its bubble canopy and 650 caliber machine guns. At 1,315 horsepower at sea level, it can pull the Mustang to 437 miles per hour and sustain combat operations up to 40,000 feet. Range with drop tanks exceeds 2,000 miles. That means P-51s can escort American bombers from England to Berlin and back. The entire strategic bombing campaign becomes viable. Those engines escort American bombers deep into Germany. The Luftwaffe calls it der amerikanische Rohrvogel and learns to fear the sound of Merlin engines at altitude. When P-51s appear over Berlin for the first time in March 1944, it's a psychological shock to German high command. The Americans can now attack anywhere, anytime, with fighter escort all the way to the target and back. German fighter losses skyrocket, experienced pilots die. Fuel becomes scarce, training degrades, Allied air superiority becomes absolute. By the time production ends in 1945, Packard has built 55,523 Merlin engines. More than all the Rolls-Royce factories in Britain combined. More than anyone thought possible when the project started. Each one built to specifications tighter than the originals. Each one perfectly interchangeable with British engines. Each one a testament to what American manufacturing could achieve when necessity demanded the impossible. The Packard Merlin represents something profound in engineering history. It proves that precision and mass production aren't opposites. They're complementary when you understand the underlying principles. Rolls-Royce built exceptional engines through craftsmanship. Packard built exceptional engines through systems. Both approaches work, both have merit. But only one could scale to the demands of total war. Only one could produce thousands of engines per month while maintaining microscopic tolerances. The techniques Packard developed become fundamental to modern aerospace manufacturing. Precision casting, statistical process control. Dedicated tooling for consistent quality. Tight tolerances designed for interchangeability rather than hand-fitting. When you fly in a Boeing or Airbus today, the jet engines are manufactured using descendants of the same principles Packard pioneered in 1941. The precision required for modern turbofan engines far exceeds what Merlins needed, but the philosophy is identical. The bearing technology Packard developed influences post-war automotive engineering. Those silver lead-indium bearings, with their superior load-carrying capacity and reduced friction, become standard in high-performance engines. Racing engines, marine engines, industrial power plants. The metallurgical innovations ripple outward through entire industries. Even the thread compatibility story has modern echoes. Today, as international standards like isometric threads exist precisely because engineers learned from World War to that incompatible fastener systems create impossible logistics problems. When American, British, and Allied forces tried to maintain equipment with incompatible thread systems, the difficulties were enormous. Modern standardization efforts trace directly back to those wartime lessons. But perhaps the most important legacy is philosophical. Packard proved that you could honor tradition while embracing innovation. They didn't discard Rolls-Royce's wisdom. They didn't arrogantly assume American methods were superior. They translated British engineering into a different industrial language. They kept the British thread specifications not because they had to, but because engineering integrity demanded it. They respected interoperability, standardization, making systems work together. That respect shapes how we approach global manufacturing today. Several Packard Merlins still fly. The Canadian Warplane Heritage Museum's Lancaster bomber in Hamilton, Ontario uses for original Packard engines. At Reno Air Races, unlimited Class P-51s with modified Packard Merlins produce over 3,800 horsepower, nearly 3 times the original specification, still perform. Still demonstrate what American engineering achieved when necessity demanded the impossible. The P-51 Mustang earned its reputation as perhaps the finest fighter aircraft of World War II, but its secret, the reason it could dominate the skies over Europe, wasn't just the airframe, or the pilots, or the tactics. It was an engine designed in Derby, England, and perfected in Detroit, Michigan. An engine that represented the best of two engineering philosophies working together. The Packard Merlin story isn't about one country's engineering being superior to another's. It's about complementary strengths creating something neither could have achieved alone. British innovation created the Merlin's revolutionary design. The two-stage supercharger, the intercooler system. The precision manufacturing standards, American manufacturing genius made it available in the quantities were demanded. The mass production techniques, the statistical quality control. The perfect interchangeability. 14,000 parts, 6,000 new drawings. 11 months of intense engineering work. The result changed the course of history in ways that still echo today. Every time a modern aircraft engine starts, every time precision components fit together perfectly without adjustment, every time engineers from different countries collaborate on complex projects, the legacy of Packard and Rolls-Royce working together continues. The next time you see a P-51 Mustang at an airshow, listen carefully to that distinctive Merlin howl. You're hearing the sound of two engineering philosophies working in perfect harmony. British innovation and American mass production combined to create something neither could have achieved alone. You're hearing the sound of impossible problems being solved. You're hearing proof that respecting tradition while embracing innovation isn't just possible, it's the only way to achieve greatness.